So I want to say that I am very pleased to be here and honored to have been invited to this Fermi lecture at La Sapienza, which is a university which has contributed so much to discoveries in physics and in science in general during the last century. It's rather intimidating to talk under the picture showing Fermi and speak about Einstein, Galileo, and Copernicus that you can see here. These are scientists about whom I will talk a lot during these lectures about light. So, and I also want to say that this is the first lectures I'm giving in person in front of a large audience since the COVID pandemic. So I'm very glad to have this direct connection. And I welcome also, of course, all the people who are on the internet following the lectures. And I hope that in the next weeks, the pandemics will decrease and that more people will be able to come here in person. So I have decided to talk about the history of the science of light for many reasons. First of all, the science of light, which has culminated with the invention of the laser and all its application in modern physics, plays, of course, an essential role in basic physics and in technology. This science has been developing since the 17th century, since the time of Galileo. And it's very interesting to study the history because it has accompanied the development of modern science in general. And it has been going in parallel with discoveries which have been made by Newton in mechanics. And the science of light is connected to astronomy, to physics, of course, but also to earth sciences, to navigation, and to thermodynamics, to mechanics, and to chemistry. So by studying the science of light, one will have an overlook over all modern science since the 17th century. At a fundamental level, the interrogations about light have given rise to electromagnetism, and then to relativity and quantum physics. And of course, you know that these fields of research, these fields of science, of knowledge, have had a tremendous impact on technologies since the 19th century. So learning about light will allow us to learn about all these fields, and nowadays to learn about quantum technologies, which are promising to bring new advances in technology and new discoveries. The evocation of light will also allow us to recall the contribution of great scientists of the past and present times. Some of the scientists I'm talking about here are maybe not so well known, but they have played a very important role in the history we're talking about. I also want to stress that this course will illustrate the very strong link between basic science, which is motivated by curiosity, just to learn, to increase knowledge, and technologies and applications. And in fact, it's impossible to separate the two. You need instruments, you need technology to make discoveries of new phenomena, and these new phenomena open to new technologies, and there is a virtuous circle going from basic science to applications and back. So I also will insist on the importance of precise measurements. Physics is the science of measurements becoming more and more precise with time, and this precision is essential to discover new effects and new phenomena, as we will see. The last point I would like to stress in this introduction is the very intimate link between physics and mathematics. Galileo said in the 17th century that the natural science, the language of natural sciences was mathematics. And in fact, mathematical development, mathematical concepts have been used over and over in the physics of light, as in the physics of mechanics, for instance. Calculus has been developed to understand this. You have also the use of complex numbers. You have the use of vector algebra, all things which came from mathematical concepts and are used to express the theories of light. And we will see this constant exchange between theory and experiments, which is an essential aspect of the scientific history of light. So this is the tentative programs that I would like to follow in these lectures. About light in the 17th and 18th century, the beginning of the really quantitative study of the properties of light. Next week, I will talk about light in the 19th century, which will see the triumph of the wave theory and the birth of electromagnetism, the connection between electricity, magnetism, and optics, which is, of course, the tremendous achievement of Maxwell. Then the next two lectures will deal with new concepts which had appeared following very counterintuitive discoveries about light. One is relativity, special and general relativity in the third lecture, and the other one is a burst of quantum physics in the fourth lectures. And in these two lectures, we will see that Einstein plays a very important role. Then in the fifth lecture, I will introduce the notion of the quantum wave function and the probabilistic interpretation of quantum physics. And in the lectures on March 3rd and March 10, I will go on discussing the quantum principles, the notion of complementarity, the uncertainty relations, the difference between fermions and bosons. And on March 10, I will talk about the junction between quantum physics and relativity. I will see of quantum theories, and I will also talk about this very strange property of quantum physics, whose measurement can be influenced at a distance. This is the notion of entanglement and the relation between entanglement, measurement, and decoherence, the loss of quantum properties when systems are coupled to their environment. Then, starting on March 17, I will go on discussing the physics of 20th century, what the knowledge about quantum physics has led to. I will talk about magnetic resonance and the birth of modern spectroscopy on March 17. On March 24, I will talk about optical pumping and the birth of the laser. And then on March 31st, about high-resolution laser spectroscopy, show how the lasers have allowed to make measurements which are tremendously precise, and this has led to a lot of interesting applications. On April 7, I will discuss the fact that laser light is not only used to probe atomic system, but it can be used also to manipulate the system, to slow down the atoms, to prepare cold atoms, and to trap atoms, laser cooling and trapping. And on April 21st, I will devote one lecture to the measurement of time. And I would like to review all the progress which have been made, even during the last years, allowing to measure time with unprecedented precision. We will be comparing what can be done with microwave clocks, which are the clocks of the GPS system, and what we can do now with optical atomic clocks. Then the last three lectures will be a little bit more special. I will, in this lecture, discuss the physics in which I have been personally involved. That is the study of atoms and photons inside cavities. It is a field of cavity quantum electrodynamics. And so I will introduce the field in the first of these three lectures. The second lecture on May 5 will discuss quantum non-demolition measurements, the fact that you can count photons without destroying them, which is a new way to detect light. And this will also lead me to discuss experiments in which we have experimented with Schrödinger cat systems which are in superposition of states corresponding to different classical realities, and introduce the notion of decoherence. And in the last lecture, I will briefly review where this kind of physics can lead us, to be an introduction to quantum technologies, metrology, simulation, and computing. So this is an overview. Of course, I'm not sure I will be able to follow these lectures in this way. It's a tentative program, which is a little bit different from the one which is on the internet now. I want to say also that these lectures are inspired by a book that I have written 2 years ago, and it was published in 2020. In French, the title is La lumière révélée, de la lunette de Galilée à l'étrangeté quantique. But the book has just been translated in English, and its title is The Science of Light. It will be published, I think, this month or next month. And those of you who are interested could find it. This book describe the scientific discoveries about light, which I'll be talking about in these lectures. And it also evokes my own career in physics. I evoke the early time of the lasers about half a century ago, when the laser invaded basic science, and a lot of interesting things happened at that time. And I will also talk about my research during the last 30 years on the manipulation of simple quantum system and the use which can be made of the system for new technologies. So the first lecture will be about the early history from the origin to the 17th and 18th century. Now, I think it's obvious to say that light is absolutely essential in our life. Light carries almost all the information we get from the outside world. It carries all the information from the universe. And in fact, the science of light has started with astronomy to try to analyze the light coming from the stars and the planet and to understand the world around us. And it's clear also that we need light because light is bringing the energy from the sun. And of course, mankind has celebrated light since its origins. But of course, at the beginning, it was not scientific. It was religious or development of myths and religion and all kinds of tales about light. But the science, the first scientific knowledge about light phenomena has been acquired during the Antiquity and the Middle Ages. It remained very qualitative. And the first quantitative results started in the 17th century. What you see at the bottom of this slide is a fresco which is in the Louvre Museum in Paris. It's an Egyptian fresco which shows the sun sending light to the eyes of this princess. And the light seems to be made of small particles, a flow of particles going from one point to the other. So some people say that it is the first manifestation of the photon, the corpuscular nature of light. But of course, this is just a metaphor. This had nothing to do with science. There was absolutely no proof at that time that light was made of particles. So this story will also allow us to visit a gallery of very famous people. I have here listed the people who played a very important role in the 17th century, from Galileo to Newton, with Descartes, Fermi, and Huygens. Then you have in the 19th century, it is a century of electromagnetism. So it started with Young and Fresnel, who established the wave theory of light, and then it went on with Ørsted, Ampere, Faraday, and Maxwell. And in the 20th century, you have also a lot of very important people who played their role in quantum physics and relativity theory, going from Planck and Einstein to Dirac and Feynman. And so I'll be talking about all these people in these lectures. So just the last introductory slide, in which I will just summarize what has this history taught us about science in general, not only about the science of light, but about science in general. This, as I said already, the discoveries about light, which have become really quantitative in the 17th century, have accompanied the birth of the modern scientific method. This method consists in making observation, doing experiments, and then trying to translate this into a mathematical formalism and theory. Then the theory has to explain the phenomena which has been observed, and it has to predict new phenomena. If the new phenomena are not observed, then it means that the theory has to be changed. And there have been a constant evolution from experimental theories and back to experiments, and the theories have changed again and again. So science is not, the truth in science is something evolutive, depending upon the connection between experiment and theory, and the science of light discuss and illustrates that very well. The second point, which is stressed and which is very important, is the symbiotic connection between basic science, which is called sometimes blue sky research, which is just to acquire knowledge, and technology. And the discoveries of the fundamental properties of light have been made possible only when instruments have been developed. We see that two instruments played an essential role in the 17th century. It is the Galilean telescope and Huygens pendulum clock. And without these instruments, the science of light would not have started. On the other hand, once knowledge has been acquired, new instruments can be developed. For example, interferometers, spectrometers, all kinds of microwave sources, lasers. All this came from fundamental discoveries. And this again allowed to make more and more precise measurements and to go into this virtuous circle. Finally, I want to stress the very important connection between the science of light starting in the 17th century with relativity and quantum physics, which are the basis now of modern science, of modern knowledge in physics. And there is still something missing, the tension, the stress between quantum physics and general relativity, which has to be solved. So we are not in the end of the story, we're in the middle of this fascinating story. So let's start, and let's start with the ancient time. I'll just introduce what was known about light before the 17th century. So during the Greek and Roman antiquity, people were not so much interested in optics, but they were interested in vision. They wanted to understand how we perceive the world with our eyes. And this, for example, Empedocles, 5 centuries before Christ, considers that in fact light was emanating from the eye. The eye was sending signals to see the world. He was comparing in some ways vision to touch. When you touch something, you have to extend your hand to feel. And the eye was extending some signals outside. In fact, this is something very modern because the radar and the LiDAR, which send electromagnetic waves and look at the echoes, work in this way. But it is not the way our eye is working. So this was a wrong vision. But you find illustration of this in old poems. For example, in Homer Iliad, there is this line saying, this verse saying, Agamemnon's heart was black with rage and his eyes flashed light. So the light was coming from the eye. A few years later, Democritus, who was the father of the atomic theory, the Greek philosopher who said that everything was made of atoms, had another vision. In his view, the atoms in the matter were producing some effigies, some small pictures of the object, and these were flying towards the eye. And this vision, of course, he has also to understand why you needed light for that. You cannot see in the dark. You need the light from the sun or from luminaries. So this theory was saying that the light was used to enlarge the pores, enlarge the holes between the atoms to let the images pass through towards your eye. So it was very poetic. This idea was developed by the followers of Democritus, that is Epicurus, and then in Rome by Lucretius. In De Natura Rerum, Lucretius described vision in this very poetic way, but which has absolutely no scientific demonstration. A little bit later, Euclid and Ptolemy developed the first analysis of vision, which has to do with mathematics. Euclid, of course, which is the father of Euclidean geometry, studied light rays emanating from the eye, but he studied the geometry of light rays and tried to explain the laws of perspective. In fact, the work of Euclid was a prescient of the works about perspective in the Italian Renaissance. And Ptolemy followed up on that, and he developed some models to describe the reflection and the refraction of light going through the atmosphere, which was very important for his astronomical studies. Then there was about a period of 10 centuries in obscurity, because we talk about light, so I think we can say that. During the early medieval time, nothing much was added to this, until about the 10th or 11th century, when medieval scholars in the Muslim world rediscovered the Greek works, Democritus, Euclid, and so on, and criticized them and went beyond that. And the most well-known scholar at that time was Alhazen, who lived mostly in Cairo around the year 1000, and who criticized Democritus and said that in fact light was not coming from the eye, but light was going into the eye from the light of the sun or light of lamps. It was scattered on the objects, and the objects scattered the light into our eyes. And he gave the first theoretical analysis of the working of the eye, comparing to a camera obscura. So it was about the year 1000. Then in the following centuries, these Arabic works went back to the Western world, to Italy, to Germany, to France, but nothing much happened until Johannes Kepler at the end of the 16th century. Kepler improved Alhazen models. He studied the propagation of light rays. He made a more precise description of the functioning of the eye by just finding out the respective roles of the pupil, the crystalline, and the retina. He also described in semi-quantitative ways the working of the Galilean telescope. He was in contact with Galileo and explained how the telescope works to enlarge images of objects. And he made another important discovery about light. He discovered the fact that the tails of the comets, when the comet was going around the sun, the tails of the comet were blown away from the sun. And he said this is the radiation pressure. The light from the sun is pushing the tail of the comets away. And so he gave this first idea about the radiation pressure at a time when nobody knew what light was about. So this is about what happened before the real beginning of my story, which starts with Galileo at the beginning of the 17th century. And I want to emphasize that two instruments are at the origin of modern physics. One is, of course, the Galilean telescope, the refracting telescope, which is a tube closed by two lenses, an objective and an eyepiece. And this tube, in fact, was not invented by Galileo. It was invented in Holland, but Galileo received the first specimen in Italy, and he immediately understood that it could be improved first. It can improve the magnification and use it to observe the sky. And he invented the tripod as a kind of the holder to have the telescope fixed in position, and made the first observation of the sky with this. The second instrument is the pendulum clock. And there again, Galileo is at the origin of this clock, because as you know, Galileo found out that the oscillation, that the swinging of a pendulum give a very precise measurement of time. The oscillations, the period of oscillation is fixed, depends only on the length of the pendulum, and is highly independent of the amplitude of the oscillation. And but he had this fundamental idea, but the real instrument was developed by Huygens about 30 years later. Huygens was able to make a system, have an escape mechanism which counts the periods by the moving of handles on a dial to count hours, minutes, and seconds. And the escape mechanism was also used to provide energy. And the mass was falling down in the gravitational field of the Earth and was compensating for the losses due to the friction of the pendulum. So he got a clock which had a precision of about 10 to 15 seconds per day, which was fantastically better than the previous clocks. And we'll see that this was essential for the first discoveries about light. What I want to talk about is the first measurement of the velocity of light. The Greeks and the Arabs thought that light was an instantaneous phenomenon. And in fact, this is intuitive. When you switch on the light in this room, you don't see the light coming to your eyes. The light is immediately there. So people, until the end of the 17th century, a lot of people thought that light was instantaneous. Galileo was one of the first scientists to assume that light was propagating at a finite speed, like sound. It was comparing light to sound. But of course, it was going much faster than sound. I don't know if the experiment was really done by Galileo, but one says that Galileo tried to measure the velocity of light with an assistant. He was standing on a Tuscan hill. An assistant was on another hill. Each of them had a lantern. Galileo uncovered his light and asked his assistant to do the same as soon as he would see the light. And he hoped that by the delay between the time it takes for the light to go back and forth, he could reduce the velocity of light. Of course, the experiment was a failure because the delay they wanted to measure was much too short to be detected by the human brain. It was a few microseconds, so he did not see anything. And so he abandoned this idea, and I don't think he thought about the velocity of light anymore. But in fact, with the invention of the telescope and the pendulum, he contributed to what was going to happen half a century later. By looking at the sky, as you all know, Galileo discovered a lot of interesting features on the moon, but most importantly for our story, he observed Jupiter and he saw 4 satellites going around Jupiter. He called the satellite Medicean satellites because he wanted to honor his patron, who was the Duke of Florence at that time. And this was very important, first of all, for astronomy, because it was the first time one saw a system in which planets were going around something which was not, at that time, people thought it was, everything was going around the Earth. Copernicus said that everything was going around the sun, but here it was just a generalization. One saw that there were things going around other planets like Jupiter. And this was rather tricky because it was going against the dogma, the church dogma, and we all know about the story. But what is important in our story is the fact that these satellites going around Jupiter were measuring time. They were like clocks. And these clocks were, you could see these clocks from everywhere in the world. And so this was very important, potentially for navigation. Because if you saw the time at which one satellite was going out of the shadow of Jupiter, you knew that everybody on the Earth would see the same thing at the same time. And so if you could tabulate, for instance, the time at which the satellite's light was going out from Jupiter shadow, you would know what time it is in Paris, if the measurement was in Paris. And if you were somewhere else, you could compare the time at this place with the time in Paris. It was the first measure of longitude which became possible in this way. And this was considered to be very, very important application. So it was at that time, the Observatory of Paris was had been just built. And the first director of this observatory was Cassini, who was an Italian astronomer who was hired by the French king Louis XIV. And Cassini ordered a young scientist, a young astronomer, Romer from Denmark, to measure the period of Io, which was one of the satellites of Jupiter, to make a table of the reappearances of Io, one after the other. And in fact, the period of Io around Jupiter is about 45 hours. So it was a clock which has a period of 45 hours. And Romer started to make measurements with the clock that, for events, he was also working in this observatory had built. And what he realized was that the period was not fixed. During 6 months of the year, the period was becoming longer and longer. And during the next 6 months, it was becoming shorter and shorter, only a few seconds per day. But Romer understood what was going on, and he shows it on this picture that you can see. What happened is that during the time Io was making one turn, one revolution around Jupiter, the Earth was going away from Jupiter. And so one had to add to the period the time it takes for the light to go through the distance that the Earth had traveled during the time Io was moving one turn. In fact, if you think about that in modern terms, this is a Doppler effect. The rotation of Io is a periodic phenomenon. And if you go away from this phenomenon or back towards this phenomenon, the period appears to be smaller or larger. And this is what Romer observed. And this was a very interesting observation. In 6 months, the delay accumulated was about 20 minutes. In fact, we know now it's 17 minutes, but it was about 20 minutes. And so Romer said 20 minutes is the time it takes for the light to go along the diameter of the Earth's orbit. The big problem was that the Earth's orbit was not known. And so, again, the Observatory of Paris decided it was important to measure the size of the Earth's orbit. And for that, Cassini sent to South America, to Guyana, on the coast of South America, which was a French outpost. He sent Jean Richet, who was an astronomer working with him. This astronomer took with him a telescope, a Galilean telescope, and a clock. And his task was to observe the parallax of the planet Mars. In fact, what happens is that if you look at Mars in the backdrop of other stars, Mars will appear on the left of the stars in Guyana and on the right of the stars in Paris, or the opposite, because of this parallax, this perspective effect. And by measuring the difference, the angular difference between Paris and Cayenne, one could measure, in fact, the angle under which from Mars you see the Paris-Euclidean distance. And by trigonometry, just using trigonometric formulas, you find at which distance Mars is from the Earth at that time. Of course, for that, you have to make sure that you make the measurement at the same time, and it is why Richter needed to have a clock. And we see that this clock played another very important role in this story a little bit later on. So from this measurement, they found out, of course, they had to wait until Richter went back to Paris to compare, because there was no way to communicate otherwise. All these experiments took months and years and were very dangerous. So I think we have to recognize all the passion of these people who are ready to risk their lives just to make this kind of discovery. The distance was found to be 55 million kilometers, and it was a time of opposition. The Sun, the Earth, and Mars were aligned, and Earth and Mars were close to each other. So this gives the Earth to Mars distance, but doesn't give yet the radius of the Earth's orbit. But in fact, you can get it because you had Kepler's laws, which related the ratio of the period to the ratio of the radius. So since you know the period of the Earth, which is 1 year, and the period of Mars, which is something about 1.5 year, from this ratio you can decide to find out the ratio between the Earth and the Mars orbit. And so you have two relations: the difference between the radius, which is 55 million kilometers, and the ratio of the orbits, and from that you get the radius of the Earth's orbit and the great axis of the Mars orbit. And they found that the Earth's orbit has a radius of 150 million kilometers, which is a value close to the one we know today. And for that measurement, Romer and Huygens conclude that light's velocity, they conclude, was about 200,000 kilometers per second. The result is wrong by a factor of about 30%, but it was a good approximation. And now we know that the real value is close to 300,000 kilometers per second. What I want to stress is that these measurements were possible only because Romer had a very precise clock. To measure the difference of 17 minutes over 6 months require precision, which is about 10 seconds per day, or even less. With the clocks before this time, it was absolutely impossible to make this kind of measurement. So I just want to conclude this first part by making a comparison between the precision of Huygens' clock, which was already fantastic for that time, and the precision of clocks of today and tomorrow. The Huygens clock is a mechanical clock which beats with a period of 2 seconds. That is, it has frequencies half a hertz, and it has a precision of 10 seconds per day. Now, today, we work with atomic clocks, which are based on counting the frequency of electrons in the cesium atom. I just show here the apparatus. I don't discuss it here because we will discuss it in other lectures. But what we measure is now a periodic phenomenon which has a frequency of 9.2 billion hertz. So it's 10 orders of magnitude larger. And in fact, the precision is also 10 billions of magnitude larger, because in fact, the precision goes with frequency. If in 1 second you count 10 billion oscillations, you are 10 billion more precise than if you count only 1 oscillation per second. And so the precision is now about 1 nanosecond per day. And 1 nanosecond per day is the precision which is required for the GPS system to work. These atomic clocks are embarked on satellites. They send microwave signals to your cell phone. And from the timing of the pulses arriving in the cell phone, you can determine by triangulation where you're, it's a very kind of parallax measurement, where you are on Earth with a fantastic precision. We will discuss the GPS later, but we will see that it's not only a quantum system, but it relies on special and general relativity to work. And this was achieved around the years, as you know, around 1980. But the story is not finished. Since then, another huge improvement in precision has occurred. Now clocks, modern atomic clocks, are not counting microwave frequencies, they count optical frequencies. They are locked in an optical transition, and they count how many oscillations of the magnetic field occurs in 1 second, basically. And the frequency is 5 orders of magnitude larger than the microwave clock. and the precision is 5 orders of magnitude larger. So instead of 1 nanosecond per day, now the precision of the clock is about a few femtoseconds, 10 minus 15 seconds per day. This precision is absolutely fantastic. It means that if you had synchronized two clocks at the beginning of the universe, they would not differ from one another by more than 1/10 of a second in 13 billion years. With this precision, you can measure general relativity effects. We will see in later lectures that time elapses at a different rate depending upon the age of the gravitational field of the Earth. In fact, this kind of precision allows clock to discriminate, to see the difference with a difference of altitude of about 1 millimeter, and experiments have been doing that. So now we see that the time measured here and there differs by 1 part into the 10 to the 16, which is largely outside of this kind of clocks, and there are many interesting applications I will discuss later. So what I want to stress to conclude this part is that with this kind of precision, the 15 orders of magnitude, which have been won since Galileo and Huygens over the precision of time measurement, illustrate how much the science of light has revolutionized our means of action and observation. We can do things which are absolutely unimaginable, of course, by Huygens, but which were also absolutely impossible to imagine even by Einstein about 1 century ago. So now let's turn to the theories about light. We learn about the velocity of light, but we still don't know what light is about. And in the 17th century, there were 4 people who played a very important role to try to find out what is light about. The first was Descartes, then Pierre de Fermat, Huygens, and Newton. And so I will discuss a little bit what they have told us. Descartes, who was the father of the rational thinking, Cartesian thinking, developed a book about light called the Dioptric, in which he discussed the nature of light. And it was a rather old philosophy about light. He still assumed that light was instantaneous. In fact, it was before Roman. So he said light is not something which moves, but light is what he called a tendency of movement. He assumed that the vacuum was full of small particles, very rigid particles, which were filling the vacuum. It was the first version of what is called the ether. And he said that when light is coming at one end, on one side of the ether, by contact, it transmits the tendency of motion to the other side instantaneously. And so it made a comparison between this motion and the fact that the blind person uses a stick to sense, when he touches something, to sense the fact that something has been transmitted from one end to the other. And so he had this rather simple vision, and this was enough for him to describe the laws of reflection on a mirror and refraction. The fact that light coming onto a diopter surface separating 2 different transparent media, part of the light is reflected like on a mirror, and another part comes into the second medium. This is called refraction. For the reflection, it was very simple. Descartes used the same analogy that was used in the Greek time. He said that the light behaves like a ball which is bouncing on the floor. And we know that the ball bounces with the angle of incidence equal to the angle of reflection. And to explain that, you just have to assume that the horizontal component of the velocity, which is parallel to the surface, is not changed, whereas the vertical component is just reversed. It is going to the surface and then back from the surface at the same speed. So he used a kind of virtual ball, and he talked about the velocity of this virtual ball while he was considering a system which does not evolve in time. So it was a rather strange and paradoxical description, but it described correctly the laws of reflection. Then he decided to tackle the problem of refraction, the fact that part of the beam enters into the transparent medium, and what has been observed since antiquity is that the beam is broken. In fact, it makes another angle enters in the medium, And what happens is that the angle of refraction is smaller than the angle of incidence. The beam is turning towards the normal to the surface, making a smaller angle in the second medium than in the first. So Descartes had to try to explain that, and his theory was, his explanation was that the ball was, so to speak, sucked into the medium, required a larger speed when entering into the medium than it had in the air. This was strange because intuitively you would see that a ball coming into the water would break and lose velocity in the water, but it's the opposite which happens. So Descartes tried to explain that, and he made a comparison with a ball rolling on a soft carpet. He said, if the ball is rolling on the carpet, it will slow down more than if it's rolling on a hard stone ground. And he said the medium inside is like the solid ground, and the air is softer, so it explains why the ball is going faster. There was no calculation, it was just a kind of intuition. And from that, he got the Snell-Descartes sign law. In fact, what he assumed is that the velocity of the ball is increased by a constant ratio when the particle enters into the medium, and then this constant ratio is now called the index of refraction. And from this, by trigonometry, you find that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to this constant. And you see here the kind of drawing that he made. Here you see two beams, a blue beam which enter with a smaller angle than the red beam, but the ratio of the sine, which are expressed as the ratio of AH over GI for the red beam and Km over NL for the blue beam, are the same. And from that, this is a sine law, which in fact was discovered by Snell a few years before Descartes. Apparently Descartes did not know about that. So in France, it's called Descartes' law, and everywhere there is a Snell law. I like to call it the Snell-Descartes law. But there was no physical explanation. It was just an ad hoc assumption made by Descartes. A few years later, there was a very important contribution by Pierre de Fermat. Fermat was a lawyer working in Toulouse, and for those of you who know mathematics, he was very famous for his statement about the last Fermat theorem, which says that a to the nth power plus b to the nth power will never be equal to c to the nth power when n is larger than 2. For n equal to 2 is just a theorem, but for higher powers there is no solution. It took 400 years to demonstrate that the Fermat conjecture was true. So he was a very good mathematician, at least he had a very good intuition of mathematics, but he was also a very good physicist. And in fact, he criticized Descartes. He said it's not true. Light has a finite velocity, and it's not going faster in the medium, it's going slower in the medium than in air. And for that, he enunciated what is called the Fermat principle, and which states that in order to go from one point to another point, light is going through the shortest path in terms of time. The light takes the time, takes the path for which the propagation time is the shortest possible. It of course explains the rectilinear propagation of light between 2 points in a homogeneous medium, but it also explains the laws of reflection. If the light has to go from A to B by meeting a mirror, it's quite clear that the shortest way is the way AMB, which I've shown here, which corresponds to the angle of incidence equal to the angle of reflection. If you go, instead of AMB, you go to A, from A to N and to B, the blue path is longer than the red path, obviously. So it explains reflection. It also explains the laws of refraction. If you have to go from one medium towards a medium in which light is going slower, it's quite clear that the light has a tendency to make a longer path in the air and a shorter path in the medium. And the compromise is the path for which you have the sine law valid. You see here, the shortest path is A, M, B. And you can give this example of someone is drawing into the water, and you have to get as fast as possible to safety. It's much better to run on the beach up to the point where you're almost at the point where you will see this guy in the sea, but not quite, and then you get the shortest time to get to the person. This is exactly what happens with the refraction of light rays. It also explains the mirages, the fact that when you look at the landscape and when the air near the ground is hotter than the air above, the air is hotter, is less dense, so the light is going faster near the ground, and so the path to go from the top of the tree to your eye is not a straight line, it's kind of parabolic curved line, and the path which reach the curve which reach your eye has gives you the feeling that you are in fact looking below the ground, and the hot air behaves like kind of mirror. This is the way images are for most of the time. The last example is the working of a magnifying glass. A magnifying glass is just made of two concave surfaces with glass inside, and you know that this is making the image of a point A to image of point B. You have many passes going from A to B. The direct pass is the one for which you have the longest pass into the glass. But if you take an inclined pass, you have to go on a longer pass in air, so it takes more time, but it is compensated by the fact that you have to go for a shorter pass in the glass where the light is going slower, and the compromise means that all these passes take an equal time. And so this is an extension of Fermi theorem. It's not always the shortest time, but in fact there has to be stationary time with respect to small variation of the pass. And from that, you can find the law of optics, which Descartes found in another way. I insisted on that because this is a fantastic, a very interesting example of theories. Fermat principle implies that light has a finite velocity, which is smaller in matter than in air. And it is the first theoretical model about light which does not make any unnecessary assumption. Fermat does not talk about the ether, which is something mysterious that he knows about. He does not make any consideration other than this principle, and it shows that this principle gives a solution to problems which seems to be quite different from each other. Reflection, refraction, mirages, optical instruments, everything is explained by a very simple principle. And this was, I think, a very interesting example of the first theoretical model which are based on mathematics. In fact, on the next slide, there are many demonstrations of the fact that the Fermat theorem is equivalent to the Snellen proof. And you can give geometric demonstration, and you can also give a demonstration using calculus. And this is the one I show you here. Assume that you want to go from point A in air to point B in vacuum, knowing that the velocity of light is VA in air and VM in the matter medium. And you project A on A prime and B on B prime, and you call the A prime B prime distance, you call it L, capital L. And you have to choose at which point M light should enter into water. And the fraction of distance A prime M over L, you call it X. This is your variable X. And from that, you use the Pythagorean theorem to define the distance A to M, which is square root of A prime squared plus X squared L squared, and the distance M to B, which is BB prime squared plus 1 minus X squared L squared. From that, you get the time it takes for light to go from A to B, which is just the time it takes to go from A to M at velocity dA, plus the time it takes to go from M to B at velocity dm. And this is a function of X. In order to find the external of this, you just have to derivate this with respect to X. At that time, it was impossible to make derivation because it was not known. The calculus was discovered a few years later, but this is a very simple demonstration. So you find the condition for the external, and This gives you, shows that the ratio V over Vn after a very simple calculation is equal to sine I over sine r. So in fact, Fermat's principle entails the Snell-Descartes sign law, and the fact that I is smaller than r means that the velocity of light is smaller in the medium than it is in air. Okay, maybe I can stop here for about 10 minutes and we'll go on after the break. Thank you.